just put up here the sketch of the simple algorithm, and that is from the textbook that is now relevant for this second part of the course by Versteeg and Müller. And you have it also a link to an older edition, the first edition, in the course material. So we have now solved then for U star, now V star, that was already done. And now we are in the process, step 2, solve pressure correction equation. That we have still to derive. What we have done is we have derived a relation between U prime and the difference of between the velocity correction and the pressure corrections. So now we do that derivation similarly to get a relation between V prime, velocity component in y direction, and the corresponding pressure corrections in the y direction. So, similarly, we derive from discretized momentum equation, derive from the discretized, that is the y momentum equation, that is 19. There we have the coefficients a, capital I, lowercase j, and we want to determine the velocity component at that location. And we assume that v is now the correct one, related to the neighbors by the neighboring coefficients, and the value of the velocity component there, minus now the correct pressure, P I j minus P I j minus 1. So that is the pressure at the north and south for the control volume for V I j, times the area, we take that at A j, plus the B now is then the source term from the, let's see, that is, should be a lowercase j, it's correct. That is the source term from the volume force in the y momentum equation. Now we do the similar thing as we did before for the U. We do it now for V by subtracting from this equation equation 13, we get then equation 20. Then we have the same coefficients, but now we get then the velocity corrections for the velocity component in the y direction. That is equal to the neighbors, the sum of all the neighbors, same coefficients for the neighbors, but now we have the velocity corrections, the v prime at the neighboring nodes, minus, and here we will have now the pressure correction, the p prime at ij minus p prime at ij minus 1 times the area that we have there. And since that is the same for both for the preliminary and for the, say, the correct discretized y momentum equation, that source term does not appear here. So, and then in the simple algorithm, we do the same approximation as we did for the for u prime, that we neglect the contributions here from the neighboring nodes. So that is, we neglect these contributions of all neighbors, neighboring coefficients, and the velocity corrections v prime there. In equation 20, that is the simple approximation, then simple yields then the following, and that is 21. That we have A, I, J, V prime there is equal to the pressure difference, and that is of the pressure correction at the faces north and south of the control volume for V, that is J minus 1 prime, and that is the area that we have there, Ij. And from this equation, and the corresponding equation that we had in the end of, before the break, 18, we get then the relations between U prime, that is the velocity correction in x direction, and V prime velocity correction in y direction, and the corresponding pressure corrections. So then 18 and 21 yield then the following. And it's simply dividing by the center coefficient. So first for U, it was U I J prime is then equal, and the coefficient that we get then is called, we shall introduce there a notation for the coefficient, the area divided by the center coefficient. First here, the D lowercase I capital case J, P prime Ij minus P prime I minus 1j. In here, we assume that the D coefficient is coming from what I just said, dividing the area of the face, that is the face then either east or west, divided by the center coefficient, then in this case Aij. And the corresponding equation then for V prime, that is then here, we divide by the Aij, get the Vij prime is equal to, and that is then minus Dij times now the pressure correction in the y direction, difference of pressure correction in the y direction, that is C prime, and that is Ij minus 1. So that is then again that direction. And here the D is, let me write that here so you can see it better, where the D Ij is equal to the area that we have here, that is the D Ij divided by the center coefficient, Aij. So that is so related to that. And now we have a relation between the velocity corrections and the pressure corrections. They are then given by these equations here, 22 and 23. Now we remember equation 15, where we represented the velocity as preliminary velocity, u star for example, plus velocity correction u prime. Now we use that. So, inserting this equation 15 for the velocity components u and v, with the expressions then u prime and v prime coming from 22 and 23, that is using the simple approximation, and similar expressions that would be for, we do it for uij and for vij. And similar expressions we would use them for the u prime at I plus 1j and for v prime at I j plus 1. So if we insert these approximations then into the continuity equation, that yields the following. That is the following. Let's see. What do we get? We get at the phase, let's see, now maybe it's better to look again at the this example here. So, because we are now considering the center control volume, where we have P in the center, and we have here our velocity u I plus 1j. And there we compute the mass flux through that boundary, and then we subtract the mass flux at the western boundary, add the northern mass flux, subtract the southern mass flux. And that is what we do now. And this net mass flux then should be 0. That is the continuity equation. So we start with the eastern phase that is indicated there, ui plus 1j. And this ui plus 1j is the u star at this point, at that point, ui plus 1j plus the u prime. And the u prime we get from the corresponding formula to 22 at this location. So we just have to increment here at the I plus 1 and then use this formula. So the u prime is then minus d I plus 1j times the pressure difference between, we have to increment that, and that is then I plus 1 j minus p prime at ij. So this all here, that is then indicating the flux, that is u, what we have here, that is u. To get the mass flux, then we need to multiply that by rho times the area. So let's see, if we do it now at the end here, rho times the area, that will be at I plus 1j. It's constant, so, but the area, that might vary. And we have to see whether that is the area of a face with a normal in x direction or y direction. So here's a face with a normal in x direction. Then we subtract now the corresponding mass flux that is then entering at the western face. That is then the u star ij, capital J, minus the d. And here we use now this for the u prime. dij, this, we have it here. I've derived it. That is the dij times the p prime ij minus the p prime I minus j. And that is multiplied by rho a at ij. So then we have the contributions of the mass flux in the x direction. Now we add them also for the y direction. So we continue here. So that is still belonging to this equation, what we are writing now. So now we compute the mass flux over the northern boundary. There we have the V velocity, that is Vij plus 1. And V is the V star plus the V prime. And the V prime we can get from this by just taking it, the J index plus 1. And that is then minus the D I J plus 1 times, now we have the pressure difference. J is 1 larger, that is the Ij plus 1 minus the P prime at Ij. And that is multiplied by the rho times the area, which is Ij plus 1. So then we have the mass flux of the northern, now the southern. That is minus, there we have the Vij, that is the V star Ij, minus, now we use the formula 23 for getting the V prime. That is the Vij times the P prime of Ij minus the P prime of Ij minus 1, multiplied by rho times the area, that is Ij. And all this here, so what we are discussing now is this here and this here. All this here, these four summands, they are 0. That is the continuity equation. And now we can collect the coefficients here regarding to P prime. Because remember, the U star and the V star we know. We have already determined. That was our first task that we did in the beginning. They are available. What we need is now the P prime, the pressure correction. And you can see what we will do. We will get the pressure correction from this equation. We'll do that in a minute. But when we have the pressure correction, the P prime, then we can immediately get the velocity correction using these equations. So if we know P prime, we know these D coefficients, we can directly compute the velocity corrections. And then we compute the velocity. The velocity is U star plus U prime. V star plus V prime is V. So that is the way we do it. So then we get from this discretized continuity equation, we get what is called the pressure correction equation. This gives the pressure correction equation. That is also giving the name to this class of mathematical pressure correction method. That is 24. Now we have the coefficients Ai capital J. And we will then collect all the coefficients for P prime that are related to Ij. You see here, we have here we see 1, here we see 1, here and here. They will appear then, let's see, we will just leave them. They are already, let's see, they are already on the right side. You see, for example, here this is, the D is positive, area divided by the center coefficient, which is positive. So then we have minus, minus, that is plus, so we just leave it on the left-hand side, and then we take the rest on the right-hand side. And that will be related, then giving us coefficients which are related to the western node, that is for Ij, and that is then multiplying the Pi minus 1j prime. We have then the east coefficient for, say, the cell or node Ij, that is multiplying the P prime at I plus 1j, and we have the contributions from south and north. First south, Ij times the P prime at Ij minus 1, and then we have the A north, capital N, times, that is at Ij at the P prime of the ij plus 1, capital J plus 1. And here we have also on the right hand side, we have still something left. And that is when we bring what we know, the u star times this, and the minus u star times this row, bring that all on the right hand side. Similarly, this times this times this. And that we summarize under all that by b, call it bij. So that is then, I give the coefficients directly, but let's just highlight this. This is the pressure correction equation. So now the coefficients in this equation that we just get when we order the equation that we derive from the continuity equation. So where the AW, IJ, I skipped that now, that is the equal to the rho dA, so the d is simply added to that, IJ, and the AE, that is getting values from rho dA from I plus 1j. The AS is getting rho d of ij, and the A north is getting rho dA of ij plus 1. The d's are defined as we had before. Rho is the constant density, A is the area. And the AP, that is the sum of these. So now I take this here away. So the AP, that is, as we are used to, is the sum of the neighboring coefficients A and B of these four. And the B that we have here, that is interesting. The Bij, that is the quantity that we would get by discretizing the continuity equation, actually with a minus in front. We would get the rho A u star, so it's the mass, net mass flux over the control volume with the preliminary velocity components, u star and v star. So it is I plus 1j minus rho A u star at ij plus rho area that is now v star, and that is at ij plus 1 minus the rho density times the area times the velocity component v star at ij. So that checks how well the preliminary velocity component satisfies the continuity equation. And actually we will use that quantity giving us how well the preliminary velocity satisfies the continuity equation as a criterion for the whole iteration process. The boundary conditions at the right boundary, let's see. We shall continue what we're doing now for the exercise 10, where they have Poiseuille flow. We shall continue on that. So we have flow in a channel, and then we assume that the velocity is given at the inlet, at the right. And if we know that, and we are flowing out in the ambient, we know that the ambient pressure then is constant, and the incompressible pressure, say the gauge pressure difference between the pressure and the pressure ambient is 0, then the P is then 0, and we have, if that doesn't change at the outlet, if that is the outlet boundary condition, the pressure is fixed to the ambient pressure, gauge pressure P is 0, then the P prime is 0. Then we have a Dirichlet boundary condition at the exit. So let us just briefly indicate that, the boundary conditions. So, if let's take that here as an example, right boundary has P is equal to P ambient. In our case, we would say 0, because we have then the gauge pressure. But in any case, the P prime that we have at this then is assumed to be 0. So, and then we can use this as a boundary condition. So then we can use the boundary conditions will then be that P prime at the eastern face or at the eastern fictitious node is 0. So we can use that as a boundary condition. And that is treated like a given temperature, T equal TB. You can also take this here at the boundary, that doesn't matter. Then it would exactly correspond to this here in the heat equation that we have discussed before. So that in heat conduction, when we discussed that for the energy equation, we had something similar. And if, for example, the boundary condition for at the left boundary is that u velocity is given, u is given at the left boundary, then the u prime w is 0. Let's say that is at the left boundary, that would correspond to that, is 0. And then we would have then if we use an equation 22, that is then giving us the relation between the u prime, this is the u prime, between the u prime and the p prime, we will see that it follows that the p prime at p minus the p prime at w is 0, and that means that we have here a boundary condition that the dp prime dx is 0. So then we have a similar boundary condition as we have for the energy equation when we have an adiabatic boundary condition. So then we set, in that case, the corresponding AW to 0 at the left boundary. That is then in the equation 24 that we had before. And the boundary condition that we have here, that is the dp prime dx at the western boundary is equal to 0, that is treated like an adiabatic boundary condition, let's see, where the dt dx is 0, that is the dt dx, and that is, say at west, for example, is 0 in heat conduction. So we can again use our knowledge on the treatment of boundary conditions that we acquired for solving the energy equation. We can use that here. But you see it is now such that here we have at the right boundary a Dirichlet boundary condition for P prime and the Neumann boundary condition where the velocity is given. And if we think of a channel, also V is 0 at the bottom and at the top, so then we have also Neumann boundary conditions there. Okay, so then we have the coefficients for the pressure correction equation, they are on the left. We have discussed the boundary conditions, then we can just solve it. And like we have solved the energy equation before. It turns out, if we would analyze this here in more detail, that this is an elliptic equation that we are solving for the pressure correction. It's a Poisson equation, essentially. Second derivatives of P prime in x plus second derivatives of P prime in y is equal to some right-hand side, which is given by the negative mass flux balance for the preliminary velocity. So, when we have solved this equation, so that the pressure correction is obtained, and we can use again to do that our favorite method, for example, alternating line Gauss-Seidel. The pressure P star is corrected. That was the preliminary pressure, P star, that we had guessed in the beginning, and that was the latest iteration in the iterative process. That is corrected. And but instead of 14, now it's coming what I already told you about earlier. But instead of correcting it directly, that is P star, P is P star plus P prime, under relaxation is used. It turns out that is better because in this process that we have been doing, we have made an important approximation. It is a simple approximation. When we derive the relation between velocity corrections and pressure corrections, there we made an approximation. It turns out that then it is favorable to use under relaxation also to correct the pressure. And that is the following. That is that we say the pressure that we finally get after this iteration is the preliminary one plus only a fraction of the pressure correction P prime. And many people, well, it was actually Raithby and Schneider who advocated to use here alpha P as 1 minus alpha U. So in our case, if we used alpha U 0.8, then this alpha P would be 0.2. You can, if you try that, you can play a little bit around. Ferziger and Perich, they advocate here, they had already before, they had alpha U 0.7, then they get for alpha P 0.3. And when we have the pressure correction, then we can, using equations 22 and 23, get the velocity corrections, and then we can correct the velocity. And for that we don't use under relaxation because our derivation is based on the representation of the velocity as preliminary plus correction. And only for that we get that the continuity equation then is satisfied. So with the pressure correction P prime, so velocity corrections, U prime and V prime are obtained from equations 22 and 23. Those were essentially the simple approximations, respectively. And then we have U prime and V prime, and then we get the velocity is then corrected using 15. That is then, just to remind you, because U is U star plus U prime, and V is V star plus V prime. So, and then we have the new update for the pressure and for the velocity. And that here is done, I stress it again, I said it already, without underfixation. Because, as I said, this relation was used to derive the pressure correction. Okay. If other transport equations are directly coupled to the momentum equations, for example, if you have the thermal problem where the density, where you have buoyancy, where the density is dependent on the temperature, then we would need to solve this at that point the energy equation to get the temperature to be able to update the buoyancy force in the momentum equation. Otherwise, if they are uncoupled, we can just do the computation of the steady Navier-Stokes equation and then solve for the scalar equation, for example, the energy equation, in the end. But often it is just coupled. So the convergence, let's see if we go back to the general simple form. So this is now the, we have now reached step 3, and I mentioned step 4, solve all other discretized transport equations. So that would be at this point. And that we do as we have learned before. The difference is that now U and V, the velocity components that we need, are computed. So we take them, the ones that we have computed here. Before we assumed them to be given, or now in exercise 10 we assume Poiseuille flow, where we have a given profile for U and V is 0. But here we take the computed ones, and then we solve, for example, the energy equation and other scalar equations. And then we have to check the convergence. That is now the point that we want to address now. That is the convergence of this loop here. So the convergence, I call that here of global iteration. Global iteration, I call that L. Because we are using iterations for solving for U star, for V star, and for P prime. We are always using iterative methods, but this is the whole process that I mean by global iteration. That can be checked by checking the continuity equation. By checking the continuity equation, and that is the right-hand side of the pressure correction equation. I mentioned it was the Bij. It was actually appearing as minus, well, it is the minus the mass flow over the control volume. So right hand side of pressure correction equation. And then with equation 24. And that would be then following in our notation, we call that B. So that was the B, and that iteration, we write this as this iteration level L then, that we are just at. We could check the 2 norm that we have been doing also now for the current exercise, and check that with respect to some tolerance of the how well the continuity equation is fulfilled with the initial guess. So the B is the discretized mass flow over the control volume. And that is then for each control volume, and then we sum overall and take this take the sum of the squares and then multiply by delta x delta y and take the square root. So that could be then used as a global convergence criteria. So then we go through this loop on, and when we have no convergence, that we need a couple of iterations to get convergence, then we set, you see here, the P star equal to the current P, the U star current U, V star current V, and phi is some scalar quantity, for example temperature, and then we continue the loop. And then we know how to solve the Navier-Stokes equations, including scalar equations. And that will then be the exercise 11. So we'll have a guidance hour tomorrow evening from 6 to 8.